Thanks, Piet. First of all, I would like to thank the organizers, so Trish, Subhajit, and Piet, for organizing this nice event, and also for offering me this opportunity to speak about this work. So this is a joint work with Diederik van Engelenburg, Christophe Garban, and Franco Severo, who is here. So thankfully, thanks to Gordon's talk, the kind of context of the talk is kind of set up and prepared. This is the main reason why we exchanged our slots. So I will be a bit brief about that, but of course, don't hesitate to interrupt me. So I will be in this talk interested in the study of critical phenomena in statistical mechanics, and for that, I will follow kind of the route suggested by Gordon in his talk, and I will try to study the critical exponents of a given model. It's a kind of law in statistical physics that when you have a phase transition and this transition is in some sense well behaved, you should be able to describe various quantities of interest on approach to or at the critical point in terms of algebraic laws, and the sort of exponents governing these laws are called critical exponents. So of course, in general, it's an impossible, extremely hard task to compute these exponents. I mean, in the widest generality, you never really manage to do that, except when you have some extra tools like integrability, for instance. But thankfully for us, there is some very nice observation coming from theoretical physics, which is that above the upper critical dimension DC of a model, there is some kind of simplification. And what do I mean by that? I mean that the critical exponents, they start taking super simple and nice values, which means that they match the exponents which you obtain in a setting where with no geometry, which is basically either the tree or the complete graph. So basically, you have in general, the geometry affects the values of these critical exponents, but if you go in sufficiently high dimensions, this geometry stops having this extremely hard effect to control, and you get a very nice exponent. And so the whole regime of dimensions, which is above this dimension DC, it's called the mean field regime of the model. Okay? And so when you're there and when you have this observation and you are studying a given model, you can ask a few questions which are kind of equivalent. First of all, you can ask, what is DC? How do I sort of capture it? Second, you can start trying to prove that you have indeed mean field exponents in dimension larger or equal to DC. And third question, which is to me probably the hardest, is to show that you have non-mean field critical exponents below the upper critical dimension. So these are three, I mean, they are sort of strongly related, right? Because in order to answer question one, usually you have to go through question 1, 2, and 3. And I will be restricting a bit my interests and focusing mainly on percolation models related to the Ising model. So this will be my focus in this. And just to recall maybe something that appeared in Gordon's talk, what we saw there is that a priori, for d strictly larger than 6, Bernoulli percolation is mean field. for this strictly larger than 4, Ising is infinite. And in fact, there is even a stronger thing you can say. The conjecture is really that the upper critical dimension of Ising is 4 and the upper critical dimension of percolation is 4. So the question you can ask is, you have the word percolation and Ising. When I take a look at the percolation model related to Ising, do I fall into the Bernoulli percolation type of behavior, or do I fall into the Ising type of behavior? So I want to understand that question. Okay, so that's it for what was supposed to be part 1. I will turn to some definitions. And well, since you've seen these definitions a couple of times already, I will be quite quick about it. I'll start by defining the Ising model. And for that, I will fix some finite subset of ZD, which I call lambda, and some parameter beta, and define a measure, which I call with a bracket, in terms of Gibbs weights. So here is the definition. It's a measure of plus or minus 1 valued functions on lambda. And it's weighted by a Boltzmann weight, which is given by this Hamiltonian. Okay, so far, very standard definition. Let me just stress that here it's really the nearest neighbor model that I look at. And it will be, I mean, it is quite important in what I do. It comes with a bunch of tools, which I'll describe later. So this is the Ising model with a free boundary condition. It's kind of boring in the sense that you have a spin flip symmetry. And if you want to use this model to try to describe, let's say, magnetism, you need to break this symmetry. And you have a couple of ways to do that. One way is to introduce a boundary condition. This is something that Franco did in his talk. And so it comes by adding some extra term in the Hamiltonian, which takes this form. Basically, you force the spins on the boundary of your set to align with some external configuration tau. So this is one way to do it. And the other way is to force every spin in the bulk to align with some magnetic field H. Okay? So this gives you a measure which depends on, well, this tau, beta, H, and lambda. So as always, I mean, in this talk, I will be focusing on essentially 2 boundary conditions, which are either all tau equal to 1 or all tau equal to 0. And this gives me 2 measures which I denote like that. And it's classical that I can construct infinite volume limits of these things. Okay, so the main interest of this model is that it undergoes a phase transition. And the natural order parameter to look at is the so-called spontaneous magnetization, which measures sort of the average of the spin at the origin under the plus measure. And so there is some kind of critical parameter beta C, when D is at least 2, above which your system magnetizes, and below which it doesn't. And so the magnetization is equal to 0. This phase transition is quite well behaved in the sense that the magnetization at the critical point is equal to 0. This is what we refer to as a continuous phase transition, usually. It means that typically this model falls into the category of models for which you expect the scaling hypothesis I was describing to you. And so this is due to a bunch of work which span over, well, 60 years. The first one in dimension 2 is coming from the computation of Yang. The second one in 86 holds for dimension greater than 4. It's due to Eisenman and Fernandez. And finally, one work we already heard about in Lorca's talk the continuity of the magnetization in dimension 3 and more was proven by Ising, Duminil-Copin, and C. Doravicius in 2015. Okay, so I guess that's it for presenting the model. Let me just add one thing, is that you do have, or at least expect, depending on how you view things, the fact that the upper critical dimension of the model is equal to 4. This means that rigorously we can prove that in dimension 4 and more, a lot of exponents of the model take their mean field value. And below dimension 4, we have much less knowledge, but in dimension 2, for instance, we know that they don't take their mean field values. There we have a lot of knowledge because we have additional tools. But in dimension 3, typically, we have no knowledge. We know nothing.
So how do you say that DC is not 3?
I cannot say it rigorously. What we have is kind of what there is available is a result by Tasaki, which tells you that if you assume that all your exponents are mean field in dimension 3, then you get a contradiction. But you have to assume not only that they exist, but also that they take their mean field value. It's kind of a strong assumption. Okay, so that's it for the Ising model, and I want to introduce percolation models related to it. So we've seen 2 already, and I could talk about the 2, but I decided in this talk to focus on one, which is the FK Ising model. And the other one we've seen is the random current model, but yeah, I will not introduce it here. So I will be even more brief on this definition. We've seen it in Johan's talk, so I don't want to go too deep into the details. But basically, and also in Rémi's talk yesterday, but basically, you can construct a correlated percolation measure on lambda with a boundary condition prescribed by 0 or 1 by weighting your percolation configuration with this weight, where K is like the number of open clusters in your model. And then you have a more standard weight, which I rewrite like that. And so this gives you a measure. 0 corresponds to the free measure, and 1 corresponds to the wired measure. And you've seen them already this week and last week. And so again, you can construct infinite volume limits, but now you have a very nice result, which is that the 2 infinite volume limits you can construct with either wired or free boundary conditions, they coincide at every beta. And I let their common value be denoted by phi beta. So this is due to a bunch of people. Bodino proved it in the case beta larger than beta C. Then the same result of Ising, Duminil-Copin, and C. Doravicius proved it at beta C. And then more recently, there was a very nice proof capturing everything at once by Aran Raoufi. Okay. So the interest, I mean, at this stage, of course, this is just a percolation model. It has no links with the Ising model. So the main reason why I introduced it is that there is the so-called Edwards-Sokal coupling, which we heard a lot about in Martin's talk. I will not describe it. I will just remind you the connection between FK Ising and Ising. So the first connection which I will mention is the fact that the magnetization in a box lambda is nothing but the probability under the wired measure that 0 connects to the boundary of lambda. And in fact, you can take this to the infinite volume limit, and you get that the magnetization is equal to the probability under the measure phi beta that 0 lies in an infinite connected component. So that's a a very interesting connection. And the other one I like has to do with the two-point function. You can show that this two-point function is sort of the same in the two models. So what this Edwards-Sokal coupling is giving is that the phase transition of the FK Ising model occurs again also at beta C, and that the two models, they share the same two-point function, which is some kind of strong information about the model. And now again, you may ask, what is the upper critical dimension of the model? But for now, it's a bit less clear. There is a connection which gives you mean field exponents for certain observables in dimension larger than 4, but it may be that FK Ising looks more like Bernoulli percolation than Ising. So I'd like to explore that. Are there any questions? Okay. So let me introduce now the sort of main protagonist in my talk, which is the one-arm exponent. So I told you that in dimension larger than 2, the magnetization at beta C is equal to 0, which means also by the Edwards-Sokal coupling that the probability that there is an infinite connected component at beta C is equal to 0. And that is sort of easily seen as being equivalent to the fact that the magnetization along the sequence of box lambda n, which I will define in a second, but also this sequence of probabilities, they both convert to 0. And here lambda n, for me, it's just the dimensional box, if you want, of size n. Right? If these are equal to 0, then whatever limits which allow to construct them is also equal to 0. Okay? And just to mention, this thing is, again, by the Edwards-Sokal coupling, equal to this quantity. That you have a wired boundary condition. Okay, so it's a pretty natural question now to ask, to say what is the rate of convergence to 0? And this whole scaling hypothesis that I was describing before is sort of predicting the fact that these things, they should behave like 1 over n to some exponent rho plus a subleading correction. Of course, this exponent rho, I'm not telling you that it's the same for the two quantities. I'm just telling you that they should be an exponent. And this exponent is what you call the one-arm exponent. So as you may have guessed, I'm going to try to say stuff about this one-arm exponent in these two settings. And before moving to the result, let me just extremely briefly, and to give you a bit of context, tell you what's known for Bernoulli percolation. Because it feels like it would be easier to start by answering this question in a setting where the percolation is slightly better detailed, or at least have additional properties. And this is done. And the result is that in dimensions strictly larger than 6, if you have a critical estimate on the two-point function, meaning that you know the rate of decay of the two-point function at criticality up to a constant, then you can show in a strong sense that rho is equal to 2 for all dimensions. I mean, that rho is equal to. Which means that this one-arm decay is of order 1 over n squared. And this is a result of Gadi and Asaf Narnias from 2011. Okay, I'm just saying that to give you context. I'm not going to explain the proof right now, but you have to keep this in mind. Okay. Let me turn to our results. So, yeah. Yeah, I think it would have been faster for me to actually write what it is than this sentence, but sorry? So the question was, what do I mean by the critical estimate on the two-point function? I mean that you know something like that, where this means that it's true up to a constant. Okay, so we have two types of one-arm exponent to compute a priori, because we have two quantities of interest, and I'm gonna look at them separately. So let me start with what I call theorem 1. We have something which holds in all dimensions larger than 2, although restrict a bit further. And we are looking for bounds on this quantity. So just for remind, I could also phrase that in the language of FK, right? And so what we do is that we prove first that there is a lower bound, which is valid in all dimensions larger than 2, of order T over n. The second result we get, now I restrict to dimension larger than 4, unsurprisingly, is the following. In dimension strictly larger than 4, we get C over n. And in dimension equal to 4, we almost have the same result, except that we have a small power of log, which comes in the upper bound. This is, yeah, thank you. This is admittance. Exactly. So this means that if you want to rephrase it in the question before, rho plus of D is equal to 1 for all D larger than 4, where rho plus is, let's say, the exponent rho, but for the plus measure. So let me just comment a little bit on this. So first of all, for the lower bound, there was a previous result due to Honda, Heidenreich, and Sakai, where they obtained a version of this bound, but they had to assume much more, a much weaker version. Here we obtain what's called the mean field lower bound, in the sense that it really matches the expected rate of decay in large dimension. And the second thing I want to say is that this log is not a big surprise, because we expect DC to be equal to 4. And what do I mean by that? I mean that when we work exactly at the critical dimension, which is here expected to be 4, we expect a bunch of logarithmic corrections to occur. And this reflects the fact that your model is mean field, but barely mean field. Like you still, you start having subleading divergent terms which are logarithmic and but which don't affect the critical exponent.
But do you really expect it to be like log cubed or really like log? What's
No. I mean, I expect that there is a log, right? But it's clear that it's not going to be log cubed. An even better reason for that is that we actually have the bound with a 5/2, but I thought that 3 was easier for it. So for D equals 6 in percolation, nothing is known, but you expect 2. Okay, so this was for the wired case. Let's now move to the second quantity of interest. And now I'm going to be immediately restricting to dimension larger than 6. And again, I'm going to look for bounds on the critical one-arm probability, which is this one. This time, what we're going to show is a lower bound of rate C over n squared and an upper bound, which is going to be matching in dimension strictly larger than 6, and again corrected by some logarithmic factor in dimension equal to 6. So this means that for the FK Ising model, we recover the result of Bernoulli percolation. Sorry? Okay, so it's like percolation, which starts screaming that the phi beta c should be maybe behaving from the point of view of its upper critical dimension, like Bernoulli percolation. And also I have a log at what could be the upper critical dimension, so it seems to be going in the right direction. But I could have this log because I'm not good enough to remove it in dimension 6. Possibility, right? And also I haven't told anything about what's happening in dimension 4, 5, or 3. So if I really want to say that this exponent is mean field in dimension 6 onwards, I need to keep working a bit. And this is what is done in the next theorem. Here I'm going to restrict to dimension 4 and 5. So we would have something also in dimension 3, but it's a kind of conditional result which assumes some decay on the two-point function, so I'm not going to write it. So what we get is the following. Now we only look at a lower bound, and we show that in dimension 5, it's order n to the 3/2, at least. And in dimension 4, it's order C over n with a log n, say, to the 4, some power of log n. So what does this mean? This means that rho d is equal to 2 in dimension larger than 6, but rho of 5 is at least, at most 3/2, and rho of 4 is at most 1. Actually, using the other result, you can show that it's equal to 1. Just out of some Markov property, this thing is always dominated by the thing on the left. Okay? So this means that we have identified a critical exponent, which is very natural, and for which it is mean field in dimension larger than 6, and non-mean field in dimension smaller than 6. So kind of the conclusion of that is that DC of the FK Ising model is different in the upper critical dimension of Ising.
How did you get the equality of 1 in 4?
So you have a lower bound, so you want to show that there is a matching upper bound, and I'm saying that this is bounded by that.
Ah, yeah, okay.
And so this observation is not new. It was predicted in physics by Coniglio, Chase, Mashta, and Stengel in 1999. And so we are just confirming the fact that the observation that they already made, that there should be a discrepancy in the upper critical dimension.
Romain?
Yeah.
It's extremely puzzling, this theorem. So may I ask, do you have an idea why somehow putting wire boundary condition lowers the critical dimension for FK? I mean,
I guess what it's saying is
it
that
doesn't lower the critical dimension, but it somehow fastens the reach of this mean field exponent for the one arm.
right. Do I have an idea? Well, what this means is that the wired boundary conditions are really pushing you. So if you have like, it's telling basically that if you travel a little bit in your box with the wire measure, then you're going to connect extremely fast to the boundary, but with free, you need to travel much more.
So maybe a better way to say the question is there a discrepancy between the mixing rates in dimension 4 and 5 of the wire and the free measure?
No. I don't think so. And by the way, this, but because to evaluate the mixing rate, basically you need to understand the magnetization. And actually we have a bound on the mixing rate. It's the square of the magnetization. And I think this bound is just sharp in dimension 4 and more. It's not the way to see it. I think maybe one thing which I can say is that this quantity, it's an Ising quantity. This one, it cannot be expressed easily in terms of Ising. So it's kind of a justification for why this thing, it has to be Ising anyway, and this thing, it may be slightly different. Are there any other questions? But let me say maybe that this was a bit puzzling for us too at the beginning. So it's not like we had the good intuition immediately. So in the remaining time, I'd like to explain to you how we prove hopefully all these results. And in order to attack this, I need to give you a very fundamental input, which Lorca already discussed in his talk, which has to do, I mean, which kind of justifies why we can say all these things, but we cannot say that for Bernoulli percolation. We need to start somewhere, right? And what we use in a crucial way is the fact that in dimension 4 and more, the 2-point function of the Ising model at criticality is extremely well understood. So first of all, you know that it's that there is this infrared bound of Froelich, Scheinman, and Spencer, which gives you a decay of order 1 over x to the d minus 2 for the 2-point function in all dimensions which are larger than 3. And there is a matching lower bound, which we proved last year with Hugo, which is valid in dimension 4 and more, and which has to be corrected by a logarithm in dimension 4. So I said before that in dimension 4 you have logs everywhere. This is the only place where I think you don't expect a log. And as far as I know, it's kind of a miracle. In percolation in dimension 6, you do expect a log. So this is the result, and this is what we did with, as I was saying, with Hugo, and this is what Diedrich, Lorca, and Marcin reproved in the talk we heard about earlier this week. So this is one input which you will just take for granted, which comes from all kinds of spectral properties verified by the model. And there is another input which has more to do with Remy's talk yesterday, which is that in high dimension, there is also a notion of critical window. And for the purpose of reaching the proofs, I will just vaguely describe it. Again, as Remy was saying yesterday, you can move a bit away from criticality so that in a box of size n, your model still looks critical in a strong sense. Okay? And in the case of high-dimensional Ising model, what we proved with Hugo in this same paper is that this critical window is of order 1 over n squared. And in dimension 4, it's again 1 over n squared, but maybe you allow for a small logarithm collection. correction. So basically, let me rephrase this. In a box of size n, up to beta c minus constant over n squared, my model looks critical. And I'm not telling you in which sense, because this would take us a bit too far, but you can think of it as being in the strongest sense possible. Yeah.
Do you need both the upper and lower bound on the critical window?
Yes, I need to know. It turns out there is one bound which is extremely easy.
Okay.
As always, kind of a mean field bound. And the other one is much harder. You will not see that I need both, but, but I do. So let me start by explaining you the proof of theorem 2, because I do believe that this is, I mean, at least for me, it's the most surprising result. And maybe also along the way, I will explain you theorem 3. So I will restrict to dimension strictly larger than 6 first, because in dimension 6, there is some kind of log to handle, but it's quite standard material. You can, it's not very easy to, it's not very difficult. And so what we want to show is that the one-arm probability is of order 1 over n squared. So let me start by describing how we do the upper bound, which is in any case the most interesting one because it gives you a rate of decay. Okay? So there is one tempting thing, which is to go through the Kozma-Martinez proof. Very tempting because it's very robust, but it's also very technical. It gives very precise information about the cluster at criticality of Bernoulli percolation. And the other problem is that it relies a lot, as far as I know, on exploration arguments, use of Burton-Kidd inequalities, and all these things not only may, I mean, they may not even be available for the FK Ising model, but also explorations, they behave extremely poorly in this model. So I don't really want to go in that strategy. And what we did instead is that we went, we adapted sort of the entropic method that was introduced by Vivek Diwan and Stefan Murhead in 2023. So let me illustrate it more precisely. I will explain why it's called entropic method also. But the result is as follows. It's an inequality which goes like this. So I'm realizing that I should write it here. It's E1. Okay, so what is this inequality? It's going to allow me to understand how the one-arm probability evolves as I flow towards the critical point. So really, it's telling me a bit more about, I also fix beta smaller than beta c, about the difference between these two probabilities. And the result is the following. You can bound it by c, beta c minus beta. Okay, this term is not so surprising. And then you have a square root. The first term is phi beta c of 0 connects to boundary of lambda n. This is okay, why not? Then there is a term which is chi of beta. We've seen that in Gordon-Stokes, but let me recall the definition. It's the so-called susceptibility of the model. It's also equal by the F. Edwards-Sokal coupling, let me mention, to the expectation of the size of the cluster of the origin. Maybe to appreciate this statement more. Sorry. Okay, yeah. So if I was over with my my theorem, this would be exactly the result that okay, basically they didn't apply it to this event, but exactly what they get in DM23. But we are not doing Bernoulli percolation. We are doing FK Ising. So there is an additional protagonist that come into play. There is this quantity triangle of beta C, and this is the triangle diagram. So this object, you saw it in Gordon-Stoke. Let me define it sort of diagrammatically. Each line corresponds to a 2-point function, and these 2 points, they are summed over. So it bears its name from its picture, I guess. So you have this quantity which pops up in the inequality, and the funny thing with this quantity is that it's finite if and only if the dimension is 3 larger than 6. This comes immediately from the lower bounds, which are written. So we have an upper bound. I mean, we have an entropic bound, which is only valid in dimension 3 larger than 6.
Is this working? Yeah. So why do you call it an entropic bound? Does it actually bound the relative entropy, or?
I will explain that to you in a second. So indeed, it's related to relative entropy. And the proof of this this bound is not so hard. For Bernoulli percolation, it's very easy. For Ising, you need to work a bit because your measure is more complicated, but the proof follows the same route. You use what's called Pin's-Curls inequality, which tells you that, say, you have two probability measures on some probability space and some event A, then you can bound, maybe there is a constant here, you can bound the difference in probabilities in terms of the max of the probabilities times something which you're gonna like, Trish, times the relative entropy of P with respect to Q. So this is where it bears its name. This is why we call it DC. And just to say, basically what is the proof? It's to look at the law of the cluster of the origin under beta C and beta and get a bound on this thing. And this thing, you can express it in terms of partition functions of your model, and you can run computations, compare it back to correlation functions, use correlation inequalities, and somehow the triangle pops up.
Romain?
Yeah.
Is the bound true for any FK Q between 1 and 4?
We do use correlation inequalities. So,
but that you can have an FK or that are related to Ising?
They are very specific to Ising,
okay.
So I adapt it. But, okay, so let me first say that having this triangle is sort of a strong indication that the behavior of this phi beta of C measure is related to dimension 6. Okay, there is something happening around dimension. It's only partial information, but it's kind of a hint. So from this, what do we do? If we let UN be the probability that 0 connects to the boundary of lambda n, and we fix d equals 6, d larger than 6, then we manage to prove a renormalization inequality of the following flavor. And so how do we do that? Well, it's not, it uses a bunch of stuff, and notably the near critical window estimate that I mentioned before. I'm going to give a vague proof. Okay. So let me start by evaluating this term. So what you have is this, beta c minus beta, times triangle. So let's say it's just a constant now, since we are working in dimensions 3 larger than 6. And so in order to make it effective, I need to pick a value of beta. And since there is only one natural value you can use, basically, because you want to evaluate this quantity and you want to show that it's smaller than this one, basically. That would be the dream. Well, if you're at beta c, clearly, I mean, if you're too close to beta c, they should be of the same order, so it's going to be tough to prove. But if you start deviating from beta c just at the right order, then this thing is going to start to be a fraction of that thing. And what I'm claiming by this result with Hugo, is that the good scale is 1 over n squared. So if I deviate by a large constant times 1 over n squared, this thing, if I believe in mere criticality, should be much smaller than this one. And this is the thing which kind of, this is responsible for this 1 over 10 un2 over 2 popping up here. So what I pick is this choice of beta with scale very large. And now what I use is the fact that, well, this susceptibility is very well understood. It's a result of Eisenman that it should behave like C over beta C minus beta. If you put all that together, you basically get what I announced. Okay? And from there, I mean, once you have this inequality, it's really not a hard task to just conclude and get the good rate of decay. So how much time do I have left exactly? Okay. So let me say just then a word about the lower bound and then a very quick word about the other theorem. So for the lower bound, we don't use any new technology in a way, and we use a second moment method, which is already what was used for Bernoulli percolation. Let me be a tiny bit specific with what I mean here. What I mean is that we rewrite the probability of interest as being larger than this thing, where n is just the number of points on the boundary of the box that are connected to 0. Okay? This is given essentially by Cauchy-Schwarz. And this bound is expected to be sharp if in this large dimension state. So how do we evaluate that? Well, for the first moment, it's quite easy. You just have a sum of correlation function, which you understand. For the second moment, you need to bound the probability that you connect to 2 points x and y. And this is known for Bernoulli percolation. It's the trigraph inequality of Eisenman and Newman. And usually you would just prove it by using the BK inequality. Well, it turns out that, funny fact, Eisenman and Newman did not have the BK inequality when they proved it in 84. So what they used instead was a kind of exploration argument. And while this exploration argument is extremely poorly behaved at the level of FK Ising, it's well behaved at the level of underlying random currents. I'm not going to dive into the detail, but basically you can show the following bound. It tells you that in high dimensional FK Ising, points, well, they should connect in a way in a tree-like structure, like that. Next. Okay? And if you plug that bound in and estimate on the 2-point function I gave, you get a 1 over n squared. problem is that you get a 1 over n squared in dimension 4 and 5 too. So you are lacking some tool in order to get the theorem 3. And there is a big reason behind that, which is extremely important. And again, I will come back to Bernoulli percolation to explain it. Is that in the context of Bernoulli percolation, below the upper critical dimension, this inequality is not sharp anymore. You're losing. So you need to replace the inequality you're using in dimension 4 and 5. And there is another bound on this 3-point connectivity that was shown by Nikita in his talk, and that he proved, which is sharp below the upper critical dimension. So one thing you could say is that, let me try to get his bound. I'm not going to write it, but for FK Ising. And there you fall into another problem, is that now it's a crazy use of exploration tricks and BK everywhere, so it's a mess. But for some reason, we can collect other information for FK Ising. We can use the fact that we have correlation inequalities, which are kind of given for free for us. And it's a quite funny fact that we can actually get a sharp bound on the 4-point connectivity function. And now the 4-point connectivity function, okay, I'm going to screw this up, but I guess if you do perhaps something like that, you instead of applying, Cauchy-Schwarz, you apply Holder, and you express this moment method in terms of a third moment, then this becomes relevant, and then basically you're done. So I'm not writing it, but what I can say is that the bound is like that. If you want to connect 4 points in low dimensional FK Ising, it's sufficient for you to connect them pairwise, and then they will connect automatically. This is due to hyperscaling, but okay. I'm just throwing words here, and you can ask me later. Okay, so I'm going to conclude just a very small word about the other theorem which I didn't mention. There is a big difficulty in this theorem. I mean, 2 difficulties. One is that we have a plus boundary condition, which we don't like. And the other one is that we're working in a finite set. And finite size scaling in statistical mechanics is kind of a terrible thing. It's very hard to control. What we like to do instead is that we like to work with infinite volume quantities because we like translation invariance, basically. So what we do in our proof is that we manage to compare it to an infinite volume magnetization with some H, which is well chosen. And from there, we can use the result of Eisenman and Fernandez from 86 and say that this thing, we know its order. We know it's H n to the 1/3 in dimension strictly larger than 4. So you want to prove that this is order 1 over n, you know the only candidate for Hn, right? It's 1 over n cubed. And turns out we managed to do that. So this is essentially the proof. There is way more behind it, but I absolutely don't have the time to discuss it. So just to conclude, I think the take-home message is definitely the fact that the upper critical dimension of FK Ising is not the one of Ising. And actually, it's a general phenomenon. Like if you take Q pots, you do expect a similar behavior. Even for the arboreal gas, which is kind of the 0 pots model. This anthropic method that I showed here, we also used it to reprove the result of Gadi and Asaf for Bernoulli percolation spread out. And the last nice thing is that in this work, in the end, we managed to access some non-mean field critical exponent for a very natural percolation model. And if you think about it, there are not so many settings in which you can do that. You have, of course, the GFF percolation on the metric graph, in which you have fantastic results. And you also have the recent works of Tom Hutchcroft, in which you can do long-range percolation in below the upper critical dimension. But essentially, that's kind of all what is known. So this is an interesting feature of what we do. Thank you.
Thanks a lot, Romain. So are there any questions?
Is the bound on the 4-point connectivity new, or it's a bit confusing?
Yeah, it's new. I mean, I never said, but it's very easy.
So you bound it by a constant times this product.
I mean, I really catch it. It takes a line, so I can write it.
Thank you.
So you want a bound on the probability that they are all connected together. And as I say, if you say, let's say you are in dimension 2. Well, to connect them together, you agree that it's enough to connect them pairwise, because then RSW kind of tell you for free that you have a connection. But it's the same here. That's what you expect below the upper critical dimension. So this you can just bound by an event which I will call F XYZ0, which is the event that Franco introduced in this talk, which is just the event that these points, they are connected pairwise. I mean, they are each point, in each connected component of your percolation, there is an even number of these points, which basically means that either they are connected all together or they are pairwise connected. And now this thing, by the Edwards circle coupling, it's just the 4-point function. With the 4-point function, you have a bound, which is due to Lebowitz, which tells you essentially that it's smaller than the product of the, basically any permutation of 2 points you can do. If you want to rephrase it, it's the bound that the Earth cell 4-point function is negative.
So for the first inequality, you use RSW in the near critical, I mean, in the...
So, I mean, this doesn't give it to me, but this is because I believe in that there is hyperscaling that I think that this one is sharp.
I see. Thank you.
Sorry? Yes, right, this is included. But I'm saying that I believe it's sharp because I believe that DC equals 6. That's why I don't lose things.
Okay, hear me. So in dimension 5, how far off do you think you are from a conclusion about the critical exponent? Because I guess you understand the expected number of points in the boundary that 0 is connected to very well.
Yeah. But let me just say that this 1/3 should be sharp. And the reason behind that is, again, this hyperscaling, which I was mentioning, which tells you that the square of the one-arm event, it should be comparable to the 2-point function at distance n. And how far are we? Well, that's a good question. We tried a little bit and we couldn't really, it seems that we are missing one crucial information that we didn't identify. At least it's sharp, conjecturally.
The bound on the 4-point function is, I guess, supposed to be sharp in every dimension less than 6, hyperscaling. But
Yeah.
you use the Lebowitz inequality, which I guess is not supposed to be sharp below dimension 4.
No, what's not supposed to be sharp below dimension 4 is that the ratio of the two things go to 0. Meaning that if you take the difference and you renormalize it by whatever it should be, but these when you take these 4 points far away from each other, it's always of the order of the, but it's a good question. Indeed, it's kind of counterintuitive.
Okay, let's thank Romain again.